science is the best tool we've got in its various forms to get closer to the truth. If we cannot take the human aspect out of science, but science is to be seen as a progression. Science never tells you the final story, but it tells you the best we've got.
Hello and welcome to The Frontier, a physics series where we have conversations with esteemed researchers in the domain of physics about their fields, why they do what they do, and their journey with science. Today we have Dr. Somak Rai Chaudhary with us. He's an astrophysicist and the director of IUCAA in Pune. He's known for his work in a wide range of domains including black holes, galaxy clusters, large-scale motions, multi-wavelength astronomy, and other problems within theoretical astrophysics, observational cosmology, and even data science. He got a BSc in physics from Presidency College in the University of Calcutta and a BA in physics from Oxford, following which he went to Cambridge for his PhD. He worked at the Harvard Smithsonian Center for Astrophysics, where he was part of the team that built the Chandra X-ray Observatory for NASA. He taught for over a decade at the University of Birmingham, after which he returned to Presidency University as the Dean of Science. He is now, as I mentioned, the director of IUCAA in Pune. So it is an absolute delight to have you here. Thank you so much for coming on.
My pleasure. I'm very happy to come here.
Yeah. To start with, would you like to say a few more words about yourself?
No, I think you got an introduction about me. I'm basically an astrophysicist, but I also see myself in the context of astronomy as a practicing scientist, and I see that in the context of society as a whole. So I'm very interested in the interaction between science and the arts and literature, and this is not something that I developed in my old age. They're all through my life, and so at every stage we've interacted with performing artists, people who do science writing in all forms, fiction and non-fiction, and also in terms of art in the form of painting, stuff like that. And so when people introduce somebody as say an expert on black holes, it is important to also think about how one came to be that, but also how one uses one's expertise in that you picked up in getting there, in interacting with the rest of society. So that's one of the most interesting things to me at this stage.
Yeah, I've seen the play that you acted in, I think, on the Foundation Day at IUCAA. It was definitely quite interesting. The one about just theorists. Yeah, yeah. So let's dive into
There have
it.
been many. I mean, yeah.
Yeah, great.
Yeah, that's
So,
that's of course fun stuff.
yeah,
We've done several things here at IUCAA where we've looked at the interaction between well, it's parodies of known plays or parodies of known situations in film and things like that, and added a scientific angle to it. But that's great fun and a lot of the spirit as well. But there's also stuff that goes on, which is to look at the interaction with various other art forms as well.
yeah. All right. So I think let's foray into what astrophysics personally means to you. What does your field mean to you?
I think I don't think I could be anything other than a scientist. Um, I don't know whether if I'm given the chance to come into science, whether I choose the same stream all over again. I might end up being a biologist or something like that. But science in general, I think is extremely important to me because it tells me that we need to understand the world around us. We need to find the word rational is much maligned, but I think it's very important for us to have a rational view of the world. And if you look around you, in particular, the current situation of the the coronavirus pandemic that's brought up upon us, you can see it kind of separates out people who have faith in science, believe in science, and people who are kind of look at science as an outsider, as kind of an option, they have an optional view of science, as it were. I mean, they choose to believe in science when it's convenient to them, and they do not if it is not. And it now shows, this particular situation now shows a lot of them in stark contrast. And but then this has been with us, I think, all through our lives. I think science is the quest to understand nature. And I found that the way I chose addressed the questions I was at that point when I got into the field. Those are the questions I was interested in, and could be a different set of questions now. But so that's what my field means to me.
Okay. And so over the years, what is one thing about that you've grown to appreciate more?
Well, well, this is quite an interesting question. Interesting question because one of the things that, if you look at my career, I've been all around the world, lived in England for, I don't know, 25 years. I've lived in the US. I've lived in India, worked in India, and the different systems have taught me different things. But the evolution, I think, comes from looking at science as mostly a theoretical activity, which is what I was exposed to when I was getting into science, where I think in India there is quite a lot of respect for people who can work out mathematics, who can think things in a smart way, solve things in a smart way, theoretically that is. But then, and then in many parts of science and society in India, people who actually do things with their hands are not considered to be at the same level as people who are very good at theory. And so the appreciation of the applied sciences, the appreciation of being able to transform an idea into something that's tangible, something that's a result, something that's a thing that you can use, is extremely important. And I think that is, the main evolution that has happened over my career, by looking at the applicability of ideas and learning how important that is, and then looking back and seeing how the applicability, the results then feed back into imagining better theories, imagining better solutions, and things like that. And I think that partly is because I got exposed to the international way of doing science, the international collaborations, the other cultures, how other cultures do science. I'm not saying that staying within India, I would not have encountered it, but it made it easier for me myself to go from a theoretical background to a mostly applicable background.
Okay. So you mentioned that you got the exposure to other cultures. So what was your very first experience with scientific research? And how is it different from everything that came before, all the education that went into it?
No, well, there are two stages. It's very important because, I went to presidency college, as you mentioned, as an undergraduate in the early 80s. It was a time when, in India, there is this big dichotomy between universities and institutes. So research doesn't happen in universities. Now it is coming in some way, but traditionally it never did. And it was a big mistake of Indian policymakers post-independence of keeping the institutes away from. So the institutional outreach was almost non-existent in the 70s up to the 80s. So the research institutions never let in young students to see what they're doing. We grew up, and it's different for you because now things are much more out in the open. Now we have the internet. Now we see a lot of stuff. We didn't have that when we were undergraduates. So We didn't have any research at all. Of course, in presidency, we had great researchers teaching us, very unusual because we had Amol Rai Chaudhuri, who's one of the most famous relativists ever
Yeah.
in the world, teaching us first electromagnetism, right? And so, but he didn't. Well, he actually in the third year taught us relativity, which general relativity, which is unusual. But we didn't get a glimpse of his research at all. So my first experience, because I got a scholarship called the Jagadish Bose National Science Talent Search Scholarship in Kolkata, still there. And one of the great things they did was they took the bunch of the year scholars, and there are 10 of them at that time. Now there are many more per year. And so the current number of scholars, say 30 or 40 of them, and they took them on third class train um, for a month every year to visit some part of the country, to visit research institutions and industry. So one year we went down to the south and we visited the Kalpakkam nuclear power station. We went to Sriharikota, we went to Madras IIT, we went to Bangalore to the Indian Institute of Science, etc., etc., etc. One year we came to Pune here. We went to Bombay to the Tata Institute. One year we went to Delhi and Jaipur and stuff like that. Great fun. And so all these people on a train traveling for a month and meeting researchers. In this particular trip and down south, I first went to the Uti Radio Telescope, met Professor Govind Swarup, who sadly passed away last week, as you know. And Govind Swarup had just made this amazing world-beating radio telescope in Uti. And he was jumping around showing us. It's such amazing energy. And this is the first time I'd seen a practicing physicist. And he wasn't afraid to come up from Bangalore to Uti for a bunch of second year undergraduates, showing them this thing that he had made, which I thought was absolutely fantastic. I don't think if I went to visit the Dunlop, tire factory, which we did from school, the boss would come down and jump around and show us how the tires were made, right? So I thought that and that enthusiasm was absolutely fantastic. And then we visited the Raman Institute in Bangalore, where V. Radhakrishnan, C.V. Raman's son, was then the director. He was also one of these people who actually built some amazing radio telescopes. Some of the biggest radio telescopes in the world are built by him. Owens Valley, Parkes Radio Telescope, things like that. And then come back to India and built the Garuvidana Radio Telescope. And then Dr. G. Srinivasan, who was his co-worker, who worked on millisecond pulsars. So just getting to see them in action was absolutely amazing. So as soon as I went back, and this was, I was in my second year as an undergraduate, I wrote to them saying, I want to come and spend time with you. So, but these institutes didn't have any kind of visiting students, interns, research, whatever, nothing, no system at that time. But Raman Institute took the bold step of inviting me for the whole summer, the next summer, and letting me hang out with the researchers. And I was probably their first research intern or whatever. I mean, they didn't have any system. I stayed in their hostel and I just, attended group meetings, saw what you would do. Some people gave me things to do. I would do little things with them. This was my first, taste of research, changed my life completely. I mean, I would, both the Uti experience and the RRI experience. And that's when I decided I wanted to do astronomy. I mean, of course, I had always had an interest in astronomy, but just to see how world-beating research is being done in India, which nobody knew. I mean, the general public didn't know about this. I mean, even now, I would say a lot of the general public do not know about how much world-beating science is done in India. And my generation just went abroad as a matter of rote, saying this is what we need to do, without knowing there was so much going on in India itself. And so this was my first, but though in this particular exercise I did not do much research myself, I came into contact with the excitement of research. I think this is not done. I mean, I think this is a thing that a lot of the institutes should do: bring people young people in to see how researchers work. That researchers are not really I mean, I remember in Ayuka we have a very big outreach program, and one of these Science Day open days, we have a science drawing competition. And many years ago, we had about 300 people, school kids, high school kids. They were asked to draw a scientist. And so it was very interesting, stunning to see out of these 300 people, about 90% of them drew a very old man looking like Professor Calculus with a lab coat and mixing colored liquids from one test tube to another, right? So this is, or looking through a telescope. And that I found, and that hasn't changed. I think that is the general public's idea of a mad scientist or a scientist or somebody who's kind of odd and has to be male and old. Whereas if you look at the typical scientist now, she's probably female. There are more women in science, if you take biology and mathematics in it, than men. It's probably in their 30s, sitting at a computer, working on something, right? So the perception is different. So at that time too, I mean, the perception that there are a lively bunch of people who do research and have fun at it is something, is a message that is not given to young people. And that is why people in general are often swayed by peer pressure into careers or by parental pressure into careers where they allow other people to tell them what to do because they have not felt the fun of choosing a career like this themselves. And I was very fortunate that I had that exposure. And it's entirely due to my scholarship group that let me do this. And of course, that was just the beginning. And then when I went to Oxford as an undergraduate, I did my second undergraduate degree in Oxford. The first summer, I took up a job as a research assistant and did my first bit of research where I actually wrote my own code. I did a computer simulation. In those days, computers were very primitive in the 80s. But that's doing hands-on stuff. But there it was natural. I mean, I was in a research group, and undergraduates would go into a research group. Nobody would think twice about it, but that culture did not exist and still largely does not exist in India, I think.
Yeah, definitely. So you mentioned all of this was really about your trajectory. So, I mean, in hindsight, would you say that a lot of it was consciously shaped by you, or was it shaped by where you were and the environment around you? How much of it can you choose to control?
Well, it's a mixture of both. I think at every point we have many trajectories, and often you then look at the roads not taken, and think of what would have happened if you did this or did that, etc. And I see a lot of my friends doing that, and I think that too. There was part of me that was determined to go into pure science and education in general. My father was a professor, and all his friends. My mother also taught in a college. So I could see a lot of academics around us. I knew that I would be in academia. There was no question about it. But then the kind of trajectory one follows is where one goes. I was very fortunate that I got a scholarship to go to Oxford, and that's how my career abroad took off. If I hadn't got that, then I would have continued studying in India, and many of my friends have done amazing work by never going abroad. So that trajectory, the detail of the trajectory is not that important. What is important is where you get to make that choice. A lot of people get pushed into careers. I did not let myself do that, and I have my parents to praise for that they never pressured me to do such a thing. Even though most of my friends went into engineering or medicine, and they've had fulfilling careers, I knew that. So that there was a choice there that was made by me. Then things happened, and there were, for example, then there were places where there were choice. For example, at the end of my undergraduate degree at Oxford, I had a choice of going to the US to do my PhD. I got into places like Harvard, Princeton, Berkeley, the top places. And also I got to Cambridge. So there was a big decision to make. And I chose Cambridge. And gosh, that was probably the best decision I've made. But a lot of my friends would immediately think of going to the US because that was what other people were doing. So such choices always happen. And then I chose to come back. I came back to India, then went back out again to the UK, came back again, things like that. So at those points, those were choices. When you're in control of your career, when you've got your first job, and then you can choose between jobs. But when you don't have control, is at your age or slightly later, when there's infinite possibilities, and then you get often influenced by um, factors that you don't choose to control, right? So I think for everybody there is a mixture, but very few people are proactive in making things happen for themselves early on in their career, and later on they are much more in control. But then the damage has been done, or whatever, or the trajectories have been taken, right? So it's like collapsing the wave function, if you understand it right.
So, did you ever know that? I was looking at a few of the topics of the papers that you published, and it seems like you're working on a lot of large scale stuff like galaxies, clusters, at least some of the recent papers. So, did you know that you would end up working in problems that like just generally speaking, obviously you've published hundreds of papers, but did you know you would end up working in those kinds of problems when you were entering astronomy?
No, not really. No, no, no. That those things also again often happen to you. I'll give you an example. For example, my first exposure to research, as I said, was at the Raman Institute when I was essentially shadowing a bunch of researchers who were working on pulsars. And because the first millisecond pulsar had just been discovered, something that's rotating 1,000 times a second, as a whole star, a neutron star. Just the mind-boggling idea of that happening was just fantastic. And the bunch of people that I had just met, Radhakrishnan and Srinivasan, were the first people in the world to find an explanation for that, of how you could actually make these things. And they just published the paper when I first met them. And that is what they were so excited about, and I got very excited. So, my first inclination would have been to work on compact stars, neutron stars, black holes. I mean, that kind of stuff. And I thought I would, and I did a little project on it. Then when I went for a PhD, I looked around to see who works on neutron stars, and and then I went to Andy Fabian in Cambridge and said I want to work on neutron stars. He said, okay, yeah, I've got all these problems, etc. But then I thought, why am I restricting myself to just that? And then I looked around and looked at various other people who were doing work. Cambridge gave me that chance of for 6 months to decide. I did a little bit of work with Professor Martin Rees, very famous cosmologist. I did a little bit of work with Andy Fabian, and then finally I decided I wanted to do because I like classical mechanics a lot, to galaxy dynamics. So I moved from neutron stars to galaxies, and it it so happened that during my research I discovered the largest structure um, of galaxies, which
Yeah,
is
the
called,
Shapley
which I named
Shapley.
the Shapley supercluster, which are named after Shapley. And that thing just came out of my PhD thesis. And that once you go make a discovery like that and get into that kind of field, then that kind of takes over. And so then I started looking at how can I study this object? I really can't do it only with galaxy dynamics and by optical surveys, which was what I was doing at that time by looking at sky survey plates and things like that. So then I moved into X-ray astronomy. So I went back to Andy Fabian and said, look, I came to you first to look at X-ray observations of neutron stars, but I'm more interested now in X-ray observations of galaxy clusters. And at that time, the Einstein telescope had gone up. Uh, People had started to make X-ray observations of galaxy clusters and to actually measure the mass of clusters. I wanted to know how massive this Shapley supercluster actually is. That whole project lasted many, many years, where I started looking at X-ray observations. That made me move to Harvard, where the actual group that launched the Einstein telescope, I started working with them. That got involved in Chandra, which was the next big X-ray telescope. So here I was a dynamicist, really, a galaxy dynamics person, and doing optical astronomy. I moved into X-ray astronomy, and I kept on doing my optical astronomy. So I go to Chile, doing a lot of work with telescopes in Chile, because that's where, the southern hemisphere is where you could see the Shapley supercluster the best. I would do a lot of work with that. I got into infrared astronomy, trying to study, various properties of galaxies, dust, etc. Then finally, I got into radio astronomy because I wanted to study the supermassive black holes at the centers of these galaxies and these clusters. So that was a whole trajectory, and so I moved from studying that kind of stuff, galaxies, individual galaxies, to galaxy clusters, to very large structures, large scale motions, and things like that. And then, when I came back to India, I started working in IUCAA. I looked at the dark energy, um, revolution had happened. People had understood that the universe is actually made up of dark energy. I started working with theorists back again here. Varun Sahni, who's my esteemed colleague here, the great astroparticle physicist. And so I took on my first PhD student, and we started working on dark energy. So, these opportunities come. Another big opportunity came when I was at the University of Birmingham, and you would meet people from other departments, over lunch and dinner in the university cafeteria, and I started talking to computer scientists who were saying how I overheard a conversation between colleagues who were trying to figure out how to automatically determine known changes in brain activity in EEGs, and trying to relate them to certain diseases. And I thought this was exactly the same as we do when we look at the time variation of emission from a black hole binary and try to figure out, or an neutron star binary star, and trying to figure out what the binary star is like. So I started talking to them, and then grew my entire machine learning and data sciences work, which I've published a couple of dozen papers on, with computer scientists completely. There was one moment, a part of my life, where I spent half my time in the computer science department.
Yes, so I'm sorry to interrupt you, but I want to talk about this a little bit. You mentioned machine learning and astronomy. So, with the rise in prominence that we've seen in big data, and just the increased accessibility of tools for analyzing this data, and even you've spoken about emerging fields like astrostatistics, um, how much of astronomy is now turning into a data science? What proportion of it?
A very good question. I think you know um, I think it's reluctantly turning into but because it actually provides a variety of data that many other fields cannot. So data scientists have discovered astronomy rather than astronomers have discovered data science, I think. But I'll come to this in a minute. But one of the characteristics of astronomy is that it's data driven. It's very data driven. If you look at the history of astronomy, I mean, theories of the cosmos, theories of the world, of the solar system, of where the sun is and where the earth is and stuff like that, they've all come from observations, right? They've been decided by observations. People have built theories about Earth being at the center and the sun turning around it, and crystal spheres, angels turning crystal spheres, whatever, Copernicus. At some point, it's been observations that has decided, which one's true and which one's false. And that has been always, and whenever, in particularly in astronomy, because astronomy deals with unimaginable things, often there's been a discovery first, and then theorists have said, "Oh my God, let's try and understand this," rather than the other way around. In many other sciences, a theorist comes up with a model, and then they construct an experiment to verify it. Astronomy, it's the other way around. You discover something, and then that completely befuddles you, and then you start putting together theory to explain it. Pulsars, a good example. Quasars is a good example. Dark energy is a very good example. We haven't figured out what it is, but we know it exists. Dark matter, all that stuff. And so it's a data-driven science. So one has to take data seriously, and one has to understand the limits of the data. Now, one limitation that astronomy has is that, as compared to other sciences, is that we cannot go and touch our things. We can't go and repeat our experiment. There's only one universe. I can't go to the galaxy. I can't change it. So I have to depend on the information that's coming to me in various different forms of light and now gravitational waves or something like that. And I have to figure out from this incomplete information, which is highly compromised by the inherent errors of our data acquisition system. And if you're looking at interesting objects, they're at the other end of the universe, so they're very faint, they're very error prone, and much of it's missing, right? And you have to fill in the gaps in your information. So it's like a detective arriving at the scene of a murder a month after the murder has happened, and so you have some stains on the wall, some evidence here, and it's completely it's totally incomplete, and so you have to figure out what's happening. So this is a very challenging aspect, but it's very frustrating. But this is the nature of astronomy, and data sciences people love that, right? Because this is where your challenges of dealing with errors, dealing with missing data, dealing with how you verify things from various different sources. These are very unique challenges in data sciences. And this is why I'm saying the data sciences people have discovered, another good kind of data bank is medical data. Same thing, missing information everywhere, highly compromised subjective data, and you have to figure out which one's true and which one's false and which one's consistent with each other. So that is why bioinformatics is such a big field, and this is why astronomy is such a big field in data sciences. And so I moved into astrostatistics. I taught my first course on astrostatistics 2 years ago here at the University of Pune. And I was surprised to see so many people turned up. In the statistics department, they have a specialism for financial statistics and stuff like that. So I suggested, if I do astrostatistics, and we essentially use the same statistics that they use in the financial markets, but I will give only astronomical examples and see what happens. And so we taught a master's course, a couple of us, and I expected maybe 5-6 people to be interested, and we had a class of 65. So it was just amazing the amount of interest generated. So this is a subject that's taking off, and I think it's a very natural marriage between because astronomy is always a data science, but data science that was self-serving because it fed into astronomical theories. But suddenly in the last 10 years, the outside world, people who deal with data sciences in general, have realized that astronomy gives you amazing data sets.
So signal processing, data analysis, etc., are these skills that are relevant or even essential for any astrophysicist?
Absolutely. Well, depends on what you want to do, really. I have in IUCAA 20 colleagues in my faculty, and I would think there are several of them who have never even looked at the sky. Or maybe they have, but in terms of look through a telescope, and that's all right, because they are complete theorists, and so they wouldn't know Andromeda from Taurus in the sky, right? So there is that kind of astronomy, or that kind of physics, where you are completely a theoretician, and that's all right. But if you are a practitioner, if you are an observational astronomer, even if you are a data scientist in astronomy, you have to understand the basics of signal processing, of image processing, and various data activities. It's not, you're not blind coding something. You have to understand where these signals come from. And so you're using detectors of all kinds. And if you see how astronomy is divided, it's divided according to the part of the electromagnetic spectrum. right? So you have radio astronomers, you have X-ray astronomers, you have gamma ray astronomers, you have infrared astronomers, you have ultraviolet astronomers, right? More so than you have galactic astronomers and stellar astronomers and planetary astronomers, even though the latter kind of division is more natural to have. But I have done stellar astronomy and galactic astronomy and clusters and everything. And a lot of people do that, but they often learn a certain part of astronomy because the data that comes from radio telescopes is very different from the data that comes from optical telescopes. You have to be an electronics engineer, a signal processing expert to build a radio telescope, because it's there you're actually detecting electromagnetic radiation from the electromagnetic fields, because it's that Rayleigh-Jeans part of the electromagnetic spectrum where you don't detect individual photons. You're detecting the energy in the electromagnetic wave and the varying electrical and magnetic field, and thus picking up the radio signals. So a radio engineer. So there's no surprise that the big radio engineers that built the radar in the World War II then became the biggest radio astronomers and built the radio telescopes afterwards, because that's the natural progression. Whereas when you're working in X-rays or optical astronomy, you are picking up individual photons. So your detectors and your telescopes are geared towards that. Imagine optical telescopes and X-ray telescopes. You have rays coming and hitting a mirror and being reflected and focusing into an image. You can't do that with X-rays. X-rays would go right through. So an X-ray mirror has to be completely different technology. You have to have rays come and hit the mirror at very small angles, so that they don't go right through. They are slowly taken, the rays, and formed an image using a long cylindrical mirror, whereas optical mirrors are different. So, and the detectors for X-rays, which are very high energy photons, and the detectors for optical photons use completely different technology. So particle physicists become X-ray astronomers because it's their technology that's used there. Optical astronomers are people who build lenses and mirrors, and then the people who build the cameras in your phones are the same people who build the detectors for optical light. So this is where technology comes from, and so this is why also astronomy is divided into these various fields, and you have to learn a particular skill. And some people actually learn many skills, but that's these are the things you learn. And then when you try to bring the data together from all these different kinds of information, and then you are acting as the detective who's arrived after the murder, then data sciences becomes very important, because then you have to know how to mesh together the data that's come from all the different sources.
Yeah, that definitely is pretty cool. So, I mean, I want to ask you one thing. Astronomy is one of those sciences that almost all children resonate towards at some point of their childhood. There's some sort of allure thinking about, our place in the universe and those kinds of things. So, does looking up at the night sky, say like in the observatories in Chile, like you mentioned, does that allure or that charm ever wane in your career?
No, it doesn't. Absolutely doesn't. One gets a lot busier, so I go to observatories a lot less now because I have to do other things like manage an institute and supervise students and things like that. But the charm never, even now when I go to an observatory, and I do quite a lot, and I look up at the sky, it's the same charm. I won't say it. I think quantitatively it's the same. I wouldn't say that the same things you find charming, um, but the awe, the general of the expanse of the universe and the skies is just mind-boggling. The other thing is, of course, the sky keeps changing. Um, Also, you see different parts of the sky from different parts of the world. I mean, a couple of years ago, for the first time, I went to South Africa at the Cape, and just looking up at the sky in a dark spot near in the southern hemisphere, because the sky is so different. Everything is upside down, and you see different parts of the sky. That also, I mean, the things for somebody who travels the world looking through different telescopes, that itself is very interesting, that you see very different things. So no, I don't think it wanes, and I think if it does, then you're in the wrong field too. But as you said, that applies to the common person as well. I mean, I yet to find a person who is agnostic to the charms of the sky. I mean, when I say I'm an astronomer, but half of the people think I'm an astrologer, but that's different. But but most of the time, the reaction is, "Wow, the sky is amazing."
Right. So, is there a singular next big thing in astronomy?
Um, I think there are many. I think there are many. I think the in and it depends on where you are, which what field you're in. I think the big thing in astronomy now, the most fashionable thing, is finding planets around other stars and figuring out what other worlds look like. Um, when I was a student, it was non-existent. We didn't know of another planet around another star. But now, the whole variety that's coming and the kind of technology that's coming up to find the atmospheres and stuff like that, habitability and stuff like that, I think that's big. In cosmology, we are trying to understand the universe and trying to figure out, what dark energy is and what the universe is made of. That's the most fundamental question. So I think that's a very big question. I mean, there are small quibbles going on, like what the age of the universe is, whether it's 13 or 14 or 15 billion years and stuff like that. But those are small quibbles. The big quibble is what is the universe made of, and to understand that, one needs to go and look at various different sources of data, and that I find is very interesting. So these two things, to me, I think, will define the next 50 years of astronomy in general, I think.
Yeah, definitely. I want to ask you what you think about the bifurcation of philosophy and science since Newton's age, because people like Stephen Hawking, who you studied under at Cambridge, like they've made overt statements like philosophy is dead. But like people like Einstein, or like on multiple occasions, they have attributed some of their work to the inspirations that they got from philosophy. Like, what do you think about this? Is it obsolete? Does it matter anymore?
But there's a long answer and there's a short answer. The short answer is that, of course it matters. I mean, scientists are people, and so people, of course, vary in their outlook to life. Some people are philosophical, some people don't think, and they like doing what they do. And some people take their work seriously, some people don't. So there is all this whole spectrum of the approach to life. And so I think the answers you alluded to indicate more the nature of the person who made those remarks than the issue itself. I think it's impossible to separate science and philosophy. This is, for example, why the Templeton Prize is given every year for people who actually think of the connection between science and religion and philosophy and things like that. And I think that is because those are much bigger issues, and there are many scientists who work in domains that they are very good at, and they like to stick to that domain, and they acquire expertise, and they don't want to think about things outside that domain. And a lot of people have said that. Einstein was somebody who didn't, and of course he thought about very deeply uh, about much larger issues. So I don't think a scientist can afford to ignore the bigger picture at all. And there are so many places where science cannot go yet, and science does not, So philosophy is, of course, philosophy is a much maligned word as well. What do you mean by philosophy? But if by philosophy you mean the context, the larger context in which you see science as a system of knowledge, then the system of knowledge, the bigger system of knowledge, the superset, has to be much bigger.
Yeah, and I mean, when people like Hawking, they say stuff like philosophy is dead. They say it because they think it's not the right way to do science. So ironically, they are kind of engaging in philosophy of science, aren't they?
Absolutely, I think you are right, because to even make that statement is a philosophical statement. Right. So I mean, whether philosophy is dead or alive is a matter of philosophy, is a matter of debate, and at every level, people are engaging in that kind of debate. whether they call it philosophy or not. So you're right. In Newton's time, it was called natural philosophy. That is why he wrote this book called Principia, which is the mathematical principles of natural philosophy. That's the name of the book. When I went to study in Oxford, physics was just named physics. I think only a few years ago, it was still a degree in natural philosophy, right? So I think that is what physics is. We just renamed it, right?
Okay.
And so and that that just, I think, says what I wanted to say. I think science is philosophy. It's a way of looking at philosophy.
Okay, so just building up on some more philosophy, um, what does truth mean to you as a scientist? Is it scientific consensus? Is it a sound theory? Because I ask you this question because the first talk that I attended of yours was about how we thought that the universe, expansion of the universe, was slowing down, but then with later measurements we realized that it's a different truth. It's speeding up. And also you've spoken about things like this incident, for example, as C.V. Visheshwar, like the black hole man of India, like he teared up when he saw like nature reflecting his theoretical calculations of the waveforms of the black hole merger when LIGO made the detection. So what exactly does truth mean to you? Like if you can be brought to tears when you see nature doing something that you predicted, does that mean that before that it wasn't true? Something along those lines.
Well, I mean, again, it's an ambiguous word. Truth, I don't think one attains truth anyway.
So I'm like, I think I should be a little bit more specific. You're right. I should ask it in this way: is there any shred of doubt in your mind that perhaps these things that we know so exactly to exist, like black holes, perhaps it's not what we think them to be, and it is probably something else that our observations, like that whole classic example of like an elephant, you touch the leg and you touch the trumpet, something of that sort. Is there any share of doubt in your mind that the power of the scientific tools that we use, they might be wrong?
I think science is a journey, and and maybe truth is the goal. I think the journey is more important. I mean, one of my most favorite poems is by George C. Ferris called Ithaca, where he talks about the journey of Odysseus to Ithaca. He actually made this journey of many years, the whole story of Odyssey, and so once one reaches Ithaca, Ithaca might not be what you want, right? But it's the journey. Through that journey, you had all these adventures, and that's what Odyssey is about. I think science is like that, and so you go through all these trials and tribulations, and you learn new things about nature. You learn new things about yourself. You learn new things about everybody else, and this is the fun of science, I think. And so I don't pretend that we'll ever reach Ithaca. I don't pretend that we'll ever know the truth, quote unquote. If we do, we're all out of business, right? So it is in our interest not to know the truth to some extent. But the whole point is we want to get closer to the truth. And I think all the things that you just explained or mentioned is just the same. Sometimes you make a prediction, like Vishweshwara's case was fantastic actually, and I was there to see it. The fact that he saw when he first saw the gravitational wave results, and it exactly was what he had predicted, 40 years ago. This kind of moment happens in a scientist's life very rarely, and that just tells him that they've gotten just an inch closer to the truth. And this is one way that knowledge grows. I mean, the whole theory of progress of science is that you go through these processes where if the predictive power of your theory is good, and then it is vindicated by experiment, then that theory is preferred over other theories. General relativity, for example, the first bending of light, Einstein wrote a postcard to his mother saying, saying that this scientist has shown that light bends around the sun. And so Einstein was absolutely ecstatic that he had predicted something, and this was found. So that tells us, but that doesn't mean that we've got the truth, right? Because the truth is a much bigger thing. And I think that's kind of the holy grail of science. And I won't know truth if I meet it, right? So I don't know what that is. But each particular scientist has a journey, and then or many journeys. And in the journey, if you come closer to what you think is the truth, that is the basic satisfaction of science, I think. I mean, most scientists aren't paid much, so it's not the money windfall that drives us. What drives a particular scientist is to see the success of knowing more, and to some extent getting closer to the truth. It could be in another generation, it could be proved wrong, but the fact that you've predicted something or done something, and later it is shown that's what it's like, or that's closer to the truth, then that perception itself is the greatest satisfaction a scientist can have.
So since we are like talking about the scientific methodology and the essence of science, I'm curious about what you think about ideas like quantum gravity and all of these like supersymmetry things that people have theorized for so long, and they want uh, at some level it's in the interest that it does exist, and all of the billions of dollars that people spend on building colliders and all just to get find some kind of like reach have experimental reach to the predictions that these theories make. Till we don't have that kind of reach, these ideas are essentially unfalsifiable, right? So doesn't that go against like the Karl Popper's ideas of what science is? Like if it disagrees with experiment, it's wrong. Like how Feynman put it. So do you think unfalsifiable ideas, either unfalsifiable on theory, like something like the multiverse theory, something of that sort, or unfalsifiable because the lack of our technology? Do you think they are ideas not worth spending a lot of billions of dollars over?
No, not at all. I mean, I mean, your question has many sides to it, but let's talk about unfalsifiable ideas. I mean, there are certain things that are inherently unfalsifiable, like God, existence of God. You can't falsify it. You cannot, prove it. You cannot disprove it. Like what was there before the Big Bang. With current understanding of science, you cannot prove it or disprove it. Is there a multiverse? We don't know. So there, I think it's fun talking about it. It's more philosophy than science. It's more debate, human debate, and it's worth doing. But there are other things like which are not actually forbidden by science in terms of getting to know it. So, for example, we know that we can get to the era of quantum gravity by experimentation. We know that we can push the energy limit to higher energies such that we can see whether, I mean, that's how we got to know about quarks, for example, things like that, the Higgs boson, and stuff like that. I think the kind of money we spend on such experiments is tiny compared to the money that's wasted on destroying the world and wars and stuff like that. And so, as I said, I see science as a journey. It's that journey to Ithaca. And in that journey, we pick up all kinds of things, right? So in building the largest collider in the world, we found the internet. And that's why we're talking right now, right? And that's because it came out of people building CERN. And so, you never know what you discover. In space sciences, everything that's on my phone right now has come out of some astronomical experiment. The camera, the GPS, the whatever, and they're mostly done for a totally different purpose. It wasn't that the digital camera in my phone was made for the Hubble Space Telescope. It was not made for a phone. But if, for example, somebody said that, oh, the Hubble Space Telescope is not worth building, $100 million or whatever it cost at that time, because because it's too expensive. Think of what kind of technology has spun off from building it and getting it up there. And now everybody has a digital camera in their pocket in the whole world. So I think every one of these things is worth doing. It can be done unless it destroys the world, right? And so the payoff is, whether you are using it for destructive purposes, whether you are, I mean, I think we need to be very worried about whether you're destroying the environment, the climate, etc., um, and stuff like that, rather than the actual amounts of money that you spend in building the next big experiment. Uh, and even if it is an experiment that cannot be done under current technology, it's worth talking about it, because that's how we push the boundaries.
Yeah, definitely. So I want to ask you one thing about yourself. How has being the director of IUCA added another dimension to your connection or your relationship with astrophysics?
No, I mean, I think um, that's a difficult question. I think what happens is that being a director of an institution just means that you get more of a sense of where the institution will go. And and after I became the director of IUCA, some very important things happened. For example, 2 weeks after I became the director of IUCA, the first gravitational wave was discovered. 4 weeks after I became the director, India launched its first astronomical satellite, AstroSat. These two things changed completely how IUCA works, because as very soon after the gravitational wave discovery, um, LIGO India was announced by the Indian government. AstroSat started sending back lots and lots of data, which we had only access to as in an Indian astronomy community, and we were not quite prepared for it. So it fell upon me and my colleagues to figure out a way of coping with this kind of new direction of of doing astronomy, big astronomy in India. There have been other projects like Rhythm GMRT, which is a world-leading project, still is in India, run by our neighbors, NCRA here, for example. But this kind of astronomy was new to IUCA, and it was interesting to be in charge of that and figure out solutions there. The other in IUCA, one of the main things we have is the engagement with the universities and outreach. And I mean, we are the inter-university center, which means that we are here. Our raison d'etre is to make sure that all the university professors and college professors in India get, if they want to, get a chance to do research in astronomy, and they bring their students in. And during my time here, we've expanded that hugely to make sure that we now design courses that are taught all over India in various colleges. Astronomy that's not done. Like, this is why I'm talking about things like astrostatistics. I'm talking about designing little courses for engineering colleges. In astronomy, I mean, if you look at world universities, astronomy is a subject taught in all universities. In India, it is not. It is a specialism in some physics department somewhere, and one of our duties is to actually take it to a larger variety of courses and things like that. And that we've done quite a bit. And so I think that focus changed quite a bit of what I was doing. Because I've always been a university teacher. I've taught at Birmingham, taught at Presidency, and before that I taught at Harvard. But I'd never actually managed the idea of teaching and helping others teach. And so this has been a very interesting challenge.
Okay, that's great. That's very inspirational too. So I want to do a little rapid fire round for a minute. Um, all right. Do you have any book recommendations?
Hmm. Well, I can only, I mean, I can't tell you what to read. I read a lot, and I can tell you what,
What are
my
those?
favorites are. Well, look at science. I mean, if you look at physics, my favorite little books are books that talk about the history of physics in the early part of the 20th century. And one of my favorite authors is George Gamow. George Gamow was, of course, a very, very famous astrophysicist, but he wrote these amazing little books in his own unique style, which he illustrated himself. The books like Mr. Tompkins in Wonderland, which are little fantasy stories about Mr. Tompkins, visiting a country where the speed of light is very, very low and what would happen there, stuff like that. And then things like 30 Years That Shook Physics. He has a wonderful autobiography called My World Line. So those are worth reading just to see the fun of science. I read a lot of biographies, and again, that comes from the history. Uh, you know, my favorite biographies are, for example, Charlie Chaplin's autobiography or Pablo Neruda's memoirs. But in science, I think two great biographies are Newton's biography by Richard Westphal and Einstein's biography by Abraham Weiss, Subtle is the Lord. And these are, very, very interesting things to just to see how science progresses. Among modern books, I think, again, I'm very biased towards actually scientists writing science, because they often give the best account of the very few scientists can write. And so one of my most favorite books in recent history has been Kip Thorne's book on Einstein's outrageous legacy, black holes, time warps, and stuff like that. That's I would recommend it to anybody.
Right. So, extraterrestrial life in the universe exists. You can only answer with a yes or a no.
Yes, absolutely. I mean,
Okay.
I can't see why we should be the only form of life.
All right. What is your favorite piece of art in all of history?
Very difficult question. Favorite piece of art. Um, I'll have to think about it. I mean, I'm so much.
So, if it's unfair, I should just ask you what's the first piece of art that pops into your mind?
The first thing that pops into my mind is Rodin's sculptures, and maybe The Thinker, maybe The Burghers of Calais, and I pretty much like three-dimensional art, and so Rodin was one of the early sculptors I came across. There was a traveling exhibition that came to Calcutta when I was in school. And so then I've chased him around all over the world. I've been to his house, I've been to his museum, I've been to his, all the places where Rodin's sculptures are displayed, wherever I can find them. Um, yeah, so that's one answer.
Okay. All right. When humanity moves out to colonize other planets, civilization implicitly follows. Yes or no?
No, not necessarily.
Okay. What is the one piece of advice you want the viewers to walk away after watching this whole episode?
Right. So I can go back to where I started to some extent. I think one piece of advice is we were talking about how, in my life, my view of science has changed. My advice would be to see scientists as people, because they are human beings first. And so science is fallible. But then that does not mean one should ignore science, because science is the best tool we've got in its various forms to get closer to the truth. So if we cannot take the human aspect out of science, but science is to be seen as a progression. Science never tells you the final story, but it tells you the best we've got currently. And I think that's what's missing. And people get confused by looking at science and looking at sometimes various versions of explanations of the same thing, and they think everybody's confused. They are not, because that's a sign that we are moving closer to the truth often. And so when you're in science, we feel that this is a process, but often people who are outside the process of science don't see it as a process. And I think it's very important that people do.
Yeah, that is an excellent note to end on. Professor Somakar Chaudhary, thank you so much for joining us today and for this wonderful session. And thanks to our audience for tuning in. We hope to see you all in our future episodes.